everyone, this is Dr. Sirisha, working as Associate Professor in Institute of Aeronautical Engineering College. Today we are going to discuss about graphs and their representation in connection to data structures, right? So what is a graph? Graph is basically a non-linear data structures. Coming to the basic concept of what a non-linear data structure looks like. So a nonlinear data structure is a structure in which data is stored not in continuous memory locations, and the relation between a data will be with more than one data element. For example, say if a data node 1 is there, it may be related to more than one data element. Something like this is nothing but a non-linear data structure. So we can even see that it is a cardinality 1 to n, n to n. So anything which is related to more number of data elements, a database is related to more number of data elements, is nothing but a non-linear data structure. Non-linear data structures are totally divided into two different categories. One is a tree, the other is a graph. So coming to the tree, the structure which you have seen right here is a tree. Here, 1 acts as the root, whereas 2, 3 and 4 act as the children of the root, right? So in the vice versa, you can call the root as a parent also. Coming to the second one, the second category of non-linear data structure, which is a graph. A graph. Let me give a small picture of the same. Say 1, 2, 3 and 4. These 4 are known as nodes or vertices. We can call them in either way. So here 1 is related to 3, 3 is related to 4, 1 is related to 2, 2 is related to 4, 3 is related to 2. So this is a graph where each node is related to more than one neighboring nodes. So probably we can say that, we can define it as saying that a graph is a finite or non-empty set of vertices or nodes, and it is a finite possible empty set of edges. It can have any number of edges. You can have parallel edges also. You can have self loops also. Okay. So these graphs are broadly classified into two different categories. One is undirected graph and the other is a directed graph. Then what do you mean by an undirected graph? See, this is a graph in which the nodes are connected something like this. See, U, V, W and X. We can say that if there is an edge between U and V, then we can also claim that there is an edge between V and U, right? So we can say that UV is equal to VU, because there is no direction specified in this graph. Whereas if I convert this into a directed graph, you can see directions in this way. Then the edges in this graph G are X to W, then W to U, U to V. That means it's a direction. It is shown. It is a directional edges you are going to have in the case of directed graphs, right? Here we cannot claim that V to U is an edge. Both are same. The graph may have or may not have. It can be in either way, right? So here the definitions say that an undirected graph is one in which the pair of vertices in an edge is unordered. If U, V is an edge, then VU is also an edge of the graph G. Coming to directed graphs. Directed graphs is one in which H is directed pair of vertices. If UV is an edge, then it is not mandated that VU will also be an edge. It depends. If there is directional edge, then they will be equal, or else not. Right. So coming to in depth about directed graphs. Directed graph is also known as a digraph, where V is the set of elements or vertices in it, and E is the set of ordered pair of vertices. Ordered pair of vertices, mane edges. Okay, so vertices are often known as nodes, and in a directed graph, if there is an edge VW, then V is its tail and W is its head. Naming we generally call it as V to be its tail and W as its head. Okay, diagrammatically we can represent them as V arrow to W, saying that from V the edge starts and at its node W it ends. Right? And in the short form, we can combine the names of the vertices and we can write like this, VW. Okay, I hope you understood what a directed graph is. Coming to undirected graph, it is also a graph where the edges are unordered pairs, right? So the edges will be undirected and each edge may be considered as a subset of V containing two elements. Here the edges will be represented in flower brackets V, W. Here head or tail terminology will not be there, as if VW is an edge, even WV is also an edge of graph G. So, and here the edges can be in a short form can be represented with a hyphen symbol in between them, and in a short form just combine these two letters, you will get it. The names of the nodes, you will get it. Okay, this is about undirected graphs. So weighted graphs. So this is also a category of graphs. So a graph in which the edges bear a weight on it is nothing but a weighted graph. This weight can be anything, like that can be of any unit. Say if you are talking about here in the given graph, you have connected Seattle, Chicago, Salt Lake City, San Francisco and Dallas. So, and they are connected with some numerical values. These numerical values can be the units of distance or any numerical value it can be. If you are using the number of units you are going to send from source to destination, these numerical values, the weights which you use, can be of any form. Okay, so weighted graphs are the graphs which bear a weight on the shoulders of the edges, is nothing but a weighted graph. And this W is a function from E into R, where E is the edge. Okay, and R is a real number. As you have seen, 3.522, these are numerical values, right? So weighted graphs, these are weighted graphs. Paths and cycles. So what is a path? Path is nothing but the collection of vertices which come between two vertices like source and destination. For example, your path is between Seattle and Dallas. So what is the path? If Seattle is the source and Dallas is the destination, what is the path? The path can be from Seattle to Chicago, from Chicago to Dallas. This is one path. Or you can have from Seattle to Salt Lake City, from Salt Lake City to Dallas. Even this can be a path. Or from Seattle to Salt Lake, then San Francisco, then Dallas. This is another path. So you can have many paths between a source node to the destination node, right? Then what do you mean by cycle? Cycle is a path. Generally, it is a path that begins and ends at the same node. For example, if you start at Seattle, go to Salt Lake, then Chicago, again to Seattle. This is nothing but a cycle. You started at Seattle and ended at Seattle. Your source and destination is Seattle, right? That is nothing but a cycle. What is path length and cost? Path length is nothing but the number of edges which are present in forming that path. So, for example, from San Francisco to Chicago, if I travel via Seattle, Salt Lake, and reach Chicago, how many edges have participated in this path? 3 edges. So, the path length will be 3. One more example I would like to say. If I want to travel from Dallas to Seattle, from Chicago to Seattle, via Chicago, I'm going to go to Seattle. So the number of edges that participated in this path are 2. So the path length is 2. I hope you got my point. Now let's go for path cost. Path cost is only for weighted graphs. Please do remember this, only for weighted graphs. Okay? Yes. In weighted graphs, the sum of the costs or the weights on the edges of a path is nothing but the path cost. Right? So, if you are traveling from Seattle to Dallas via Salt Lake and Chicago, then path cost will be Seattle to Salt Lake is 2, Salt Lake City to Chicago is 2, Chicago to Dallas is 2.5. So the total path cost is 6.5. So this is how we are going to calculate the path cost. Path cost is nothing but the sum of the costs on the edges which are in that path. Right? So next, let's talk about the connectivity. Before going to connectivity, I would like to address a few points over here. See, as I said, graphs are broadly classified into 2 categories. One is directed, the other is undirected, right? Coming to the weights, if you want to classify in terms of weights, you can have weighted graphs and unweighted graphs, right? So, we can have combinations when you construct a graph. For example, we can have a directed weighted graph, or you can have directed unweighted graph, or you can have undirected weighted graph, or you can have undirected unweighted graph. All the 4 combinations you can have, right? So based upon the combinations, we talk about the connectivity. Right, guys? I hope I'm clear with the concept of the different types of graphs that we can have. Let's start with undirected graphs are called as connected if there is path between any 2 vertices, if there is a path. For example, have a look at the graph at which is given. One sec, let me clear the screen first. Yes. Here, what connectivity tells us is no node must be left alone or idle without connected to any other node. So you should not have any node, something like this. This node, say, let's name it as X. These nodes, let's name them as A, B, C, and so on. So X is not related to A or B or C or any other node of graph G. Okay, so such a node should not be present. If I arrange X, then the graph is a connected graph because you can see that all the nodes present in the graph are connected. Such a graph is undirected connected graph. Coming to directed graph, which is strongly connected. We call a directed graph as strongly connected if there is a path from any one vertex to another vertex. A path. Please remember, strongly connected tells us about path, not an edge. Okay, so let's me name this one A, B, C, and D. Let us check. Is there a path between AB? Yes, they share an edge. AC, they share an edge. Coming to AD, via B you have a path, or via C you have a path. So there is a path from A to all the remaining nodes. One job is done. Coming to B, is there a path between B and A? Yes, via D you can reach A. Coming to C, can you reach C from A? Yes. Let's start with B. When we start with B, you reach D first, then A, then C. Is there a path or not? Yes, there is a path. So coming to D, they share an edge, not a problem, right? So from B, we can connect to all the remaining vertices through a path or via an edge we can. Coming to C, from C, can you reach A? Yes, via D we can reach. Coming to B, yes, via D, A, you can reach B. Coming to D, C and D share an edge, not a problem, right? So here we can see that all the vertices, similarly, all the vertices are connected to the remaining vertices of the graph through a path. Such a directed graph is known as strongly connected graph. Strongly connected graph. Coming to directed graph, which are weakly connected. If there is a path between two vertices, right, ignoring their directions, right, directions, then it is a directed graph which is weakly connected. Have a look at this one. If I name the vertices A, B, C, and D, there is a path from A to C, but you cannot reach D or B, right? Coming to B, from B you can reach D as well as C, but not A. Means nodes are connected. Nodes are connected. There is no isolated node, but they are not completely connected. A node cannot reach all the remaining nodes, right? So such a connectivity in directed graphs is known as weakly connected. Okay. Then what do you mean by a complete graph in terms of directed graphs? If there is edge between every pair of vertices, then it is known as a complete graph. Please remember this point, edges. Here I am not talking about pairs, I am talking about edges. So have a look at this picture, my dears. A, B, C, D. You name the two vertices. Between every two vertex, you have an edge. You have an edge between AB and BA, AC and CA, AD and DA. And this is for all. So such a graph is known as a complete directed graph. So there will be conclude with the connectivity in terms of graphs, right? So have a deep look into the complete graphs, because here all the nodes are connected to the remaining nodes in a graph, right? So they share a bidirectional arrow to represent the same. Rather than drawing two arrows in two different directions, they have mentioned a single arrow in a bidirectional way, right? So have a look at this one. In an undirected graph with n vertices, the maximum number of edges you can have is n into n minus 1 by 2. Whereas in case of directed graphs, it is n into n minus 1. Okay, please do remember these 2 points. They are very, very important in your competitive exams point of view, say your placements or gate exam, these type of questions are very important. Please remember this, guys. So coming to trees as graphs. So when a tree is going to behave like a graph. So every tree is a graph. If you remove your edges in a graph, you can feel that it is a tree, right? So tree is a directed from top to bottom, from root to the leaf, right? So there will not be any cycles, and it is a directed path from the root to every node. Have a look at the picture which I have given. So if this is a graph from A to BC, and B is having children D, C is having only one child F is having two children GH, and G is having a single child J. If you look at the connectivity, have a look at the red marked arrows. If I draw an edge something like this, and this tree converts into a graph, it is no longer a tree. Even if the arrow, as I said, a tree is a top-down structure. If an arrow is going in the upward direction also, it is not a tree now. Or if you have an isolated node, just like it is a node, part and parcel of the graph, but is not connected to any node in the remaining nodes in a graph, then it is not a tree anymore. Okay, there should not be any cycles, any bottom-up approach, any isolated vertices. Then you can call a graph to be a tree. Remember, cycles should not be there. Okay? Yes. Coming to DAGS, directed acyclic graphs. DAG, the word itself tells you acyclic. Directed money, we are talking about directed graphs. Acyclic means zero cycles. Cycles should not be there. That means if you start at a node and try to draw a path, the destination should not be the source node. If it is a source, if you reach the source node, then you are forming a cycle, then it is not a DAG anymore. Okay, have a look at this picture. Okay, so you can see that every tree is a DAG and every DAG is a graph, right? Right. Then graphs implementation, where we can implement graphs using arrays as well as linked list. Let's first look at the implementation of graphs using arrays. We can implement them using your single dimensional or double dimensional, right? So in one dimensional array, they'll be used to store the vertices, as in the two dimensional arrays are used to store the edges. Have a look at this picture where we have connected Dallas, Austin, Denver, Chicago, Austin, Atlanta, and Washington. And you can see that it is a weighted directed graph. You can see the weight on the head of the edges, right? Right. In this representation, as I said, single dimensional array, one dimensional array is used to store the vertices, where I have mentioned the names of the cities, whereas the two dimensions one is used to store the weights. So I have 7 nodes. So I am going to use 7 by 7 matrix. That is, I'm going to use only 49 cells. But I have taken as a precautionary method, I have taken a single dimensional array of 10 cells. If it is of 10 cells, then my matrix will be of 10 by 10, 100 cells. See, my allocation, based upon allocation, it is 100 cells. Whereas I have used only 49 cells. Right? So, leftovers are 51 cells. Wastage of memory. Can you see that? Yes. So 51, more than 50% of the memory went into vain. waste. So that is the basic drawback of arrays. Basic drawback of arrays. It is whether it is single dimensional or double dimensional. And have a look at the 49 cells which I have used. So not all nodes are connected to each other. It is not a complete graph. I hope you might have seen that it's not a complete graph. So wherever there is not an edge between two nodes, I have represented that with a 0. If you go for a count of zeros in this 7 by 7 matrix, more than 50% of the cells are filled with zeros. So if in a matrix, if more than 50% of the cells are filled with zeros, we call it as a sparse matrix. So even this is the wastage of memory, which we can overcome using linked list. Let's have a look at it. Linked list representation, for which I'm going to use again one-dimensional array, which is not going to show me much memory wastage when compared to two-dimensional storage of weights, right? And to store the weights, I'm going to use linked list. So for the same graph, let's see linked list representation. Have a look at this one. One-dimensional array, I have used it to store my vertices name, and coming to the linked list, which is going to store the weights. See, each and every node is having 3 parts, right? So what are the 3 parts? The first is index of the adjacent matrix. Index of the adjacent matrix. Then followed by the middle part with the weight and pointer to the next edge. Or you can say address of the next edge, right? So Atlanta is linked to your node 5, right? So node 5 is given and a weight which is going to connect them is 800, right? Coming to the next one, and Atlanta is also sharing an edge with Washington, right? So 6 and the distance, let's say it is distance, the distance is 600, which is placed in the middle. So Atlanta is having only 2 nodes as its neighbors, 5 and 6. So the pointer part of the second node is filled with null, saying that this is the end of the list. In this way, we can reduce the memory wastage. We can reduce it by storing the weight, node name, and the pointer to the next node, the form of a node, and link the nodes of a given vertex. Then it will be easy and memory wastage will be very, very less. Okay, so these graphs can also be represented using matrices, right? So in case of, I've taken an example of undirected graph with say 7 vertices, and adjacency matrix of that can be drawn in this manner. Have a look at this one. So as 7 vertices are there, I'm going to take a 7 by 7 matrix. If there is an edge between 2 nodes, then I'm going to represent it with the 1. Say 0, 1. Sorry, let me erase it, right? Yeah. 1, 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, and 7. There is no edge between 1 and 1, right? There is no self loop. So I have taken 0. There is an edge between 1 and 2. So I have taken 1 instead, right? Instead of 0, I have taken 1. See, in the same way as it is an undirected graph, if there is an edge between 1 and 2, then it also refers to the vertices 2 and 1, saying that there is an edge between them, right? So I have marked 2, 1 also as 1, saying that there is an edge. Similarly, take any edge in the adjacency matrix. 1 will be filled if they share an edge, and 0 if they do not share. if you keenly look into this matrix, you can see that it is a symmetric matrix. It is a symmetric matrix. This is how adjacency matrix will be represented based upon the data of the neighbors, right? Neighboring nodes. So the same one in terms of directed weighted graphs. It is a bit complex one. Have a look. The matrix will not be symmetric in nature. So have a look at this one. You can observe that the diagonal elements are zeros. Why? There are no self-groups. And there is no point in saying that you can form an edge. We can form a path. By thought process, we can bring a path, but not an edge. It should be there in the graph when it is given. Okay, the initial state itself is not. It is not there. So the diagonal elements are 0 as per the given weighted directed graph. Okay, let's talk about the filling. So there is an edge between 1 and 2, which is bearing a weight 25. So I have filled that. But it is not saying that there is an edge between 2 and 1. So I have filled that cell with infinite. We may reach from 2 to 1, but right now there is no direct edge between them. So adjacency matrix will be filled with the weights on the edges, but not based upon the weights on the path. It is purely based upon edges. If there is an edge, if they share an edge, then the cell will be filled. If there is no edge, it will be filled with infinite, saying that right now there is no direct edge between them. You can make a path and fill it. So for example, from 2 to 1, if you want to replace this infinite. So from 2, you can come to 3. From 3 to 1, there is a path, not an edge. What is the cost of that path? Path cost is 15. So rather than writing infinite, you can fill it with the path data as 15, but not right now. It is just for information's sake I told. Right now we are talking about adjacency matrix. You have to fill it with infinite if they do not share an edge. If two vertices do not share an edge. Okay? This is adjacency matrix in terms of directed weighted graphs. Okay? Then array of adjacency lists. So we can have using an undirected graph, unweighted graph. We have represented the adjacency matrix. Now have a look at the adjacency lists. So here I'm going to use one-dimensional array to store the data of the vertices and a single linked list to store the neighbors data. Say for example, one is having 2 neighbors. One is node 2 and the other is node 3. And their data is linked in this way. Right? Saying that 2 and 3 are the neighbors of 1. So let me take for an example, say 6. Who are all the neighbors of 6? 2, 4, 5 and 7. 4 neighbors are there. So 4 nodes will be there. So 3, 4, 5 and 7. These are the neighbors of our node number 6. Using single linked list, we can get the data of the neighbors of any using linked list. That is specifically single linked list. If it is a weighted graph, what you are going to do? Even the weight of that graph is important. So I'm going to restructure the node by extending its wings, like previously the node was having 2 paths, the information of the neighbor and the address of the next node. It is extended with a new part, the weight, which I have included. Right? Have a look. One is having a neighbor 2 with a weight 25. Right? And it is not having any other Neighbor. Have a look at one. It is having only one neighbor, which is 2. Got it? So this is how we are going to represent adjacency lists of a given directed weighted graph. So coming to the applications of graphs. Applications, they can be used in many areas. So in computer science, graphs can be used to represent flow charts, right? Flow of computation, how data flows from one module to the other. And Google Maps, you might have seen Google Maps. Wherever you go, you put your destination and your smartphone is going to show how to travel to that area. If I'm sitting in my college and trying to travel to the airport, then what is the shortest distance, which stops I need to, how easily or how fast I can reach airport. Everything will be shown because my smartphone is already fed with maps and it is going to show me the shortest path, right? So Google Maps is based upon that. Coming to Facebook, friend suggestions. They use graph theory. So those who are familiar with Facebook, they'll be getting invitations like friendship invitations, or you can search for friends in using mutual friends, right? Mutual friends. A friend of your friend is a friend of yours. It is going to suggest you. Do you want to invite him to be your friend? So it is nothing but a graph building a node-to-node connectivity, right? So Facebook's friends suggestion algorithm is based upon graph theory, which will help you to show you mutual friends. Okay, coming to in operating systems, resource allocation graph. By allocating resources, right? So I'm working on a single process system. So my system is connected to a printer, a scanner, an external hard disk, and so many. So every other outer source, the secondary device is going to ask my processor, can you provide me this driver? Can you provide me this driver? Karke. Then it must be able to handle all this. My OS, right, operating system, is going to handle it by allocating time, a space to them, seeing that no source is going to go in a deadlock, right? It cannot make the printer starve for inference, saying that I'll provide you the resource at the last. So if it provides a printing driver to the printer, then soon it is going to allocate send some data to the external storage device to store. So all these things, it uses a graph theory to connect all these resource allocations. So in OS operating system, the students who are familiar with this subject, they can recollect resource allocation, memory management. Everything in OS will be done based upon graph theory. If you look deep, every problem can be converted into a graph. Everything is human relations are graphs, right? How we are related to each other, right? The relationships. So everything is a graph. Okay, let's come back to our technical point of view. The basic applications will be computer science, graphs, Google Maps, Facebook's OS, any social media, even you take it Twitter, any social media, Insta, wherever you find connectivity, you will find graph theory, graph algorithms behind the screen. Okay, coming to the traversal techniques. This is the last point here. So, graph traversal techniques. There are two basically graph traversal techniques, which is depth first search and breadth first search, which are used to travel all the from one node to the other and touch all the nodes. So depth first search uses stack for its implementation, whereas breadth first search uses queues for its implementation. Coming to their basic applications, so for analyzing networks, depth first search is used, whereas breadth first for GPS navigation. So breadth first, for example, if you are starting from a college, the same example I would like to take, from college to the airport, do you have only one route? You will have n number of routes. So all the n number of routes will be shown in your breadth first search. Shortest will be shown by your depth first search. So these kind of things, right? So these are the two basic graph traversal techniques that we have using graphs. Guys, I hope you understood the concept. If you have any queries, please do post me and let me know. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.